I wanted to give you a little bit more of a quantitative discussion of Faraday's law. This will accompany more or less the lecture that is on the PowerPoint that is already on the iLearn site that you could look at. But imagine you have a magnetic field here, B, and it's pointed into the board. That's what the X's mean. You can think of the X's as the back of an arrow, the feathers of an arrow. So when you see X's, it means the arrow is going into the board. And you can see the dots as arrow heads coming out towards you. That's a nice way to remember what X's and O's mean, whether it's going into the board or coming out of the board. So this is magnetic field of strength B. This is a coil of area A. And I'm going to say that the coil is spinning this way. So it's going to be spinning this way, not this way, but this way, into and out of the board, such that it would be doing this. And continually, but continually in one direction. I can't keep moving my wrist that way, I'll break my wrist. So, but imagine this coil is doing that. And the flux is given by the symbol here, phi, and it's equal to the size of the coil, the strength of the magnetic field times the area of the coil. And the area of the coil is the area that's perpendicular to the magnetic field. So right now it's the full area. But when it's like this, it's actually zero. There's zero area that's in the same direction as the magnetic field. And then when it goes this way, then you have almost like the negative. So the area of the coil is pointed in the opposite direction as the magnetic field. So we even say that the area is a vector. And the vector is pointing out from this position here. So when I'm like this, the area is pointed into the magnetic field opposite the direction of it. So that's what we can use to think about the flux. And that's where this dot product here comes in handy. That actually it takes into account that it's the cosine of the angle between the area and the magnetic field. That's what that dot tells us. So we could rewrite this as B times A cosine theta, where theta is the angle between the coil and the magnetic field, which can go between 0 and 360 degrees or 0 and 2 pi. And of course, if you have more than one coil here, if you have two coils, you'll have twice the flux. 3 coils, 3 times the flux. So the more coils you have, the more flux you have. So you can multiply this by n, and you can multiply this by n too, and that gives you the actual amount of flux for n coils rotating in a magnetic field. So that's what we could think about as a coil rotating in a magnetic field. That is going to generate a voltage. If you could have two ends of the coil here, like the coil just kind of cut there, and you have a voltmeter there that's spinning along with the coil, it's going to measure a voltage, and that voltage it's going to measure is given by Faraday's law, which tells me that that voltage is equal to the change in flux as a function of time, with a negative sign in front of it. Negative sign in some ways doesn't matter for us. It's still going to be something that varies as in some function. It's just whether it starts at one value and goes down, or whether it starts in value and goes up. Remember, it's going to be an AC value. All right, so let's actually calculate what this change in flux with respect to time is going to look like. And to do that, I need to think about what is theta doing. Is theta always staying the same? And the answer is no. If the coil is rotating, then this angle is changing all the time. The angle between the magnetic field and the coil is always changing. So we can think of the angle theta as being the angular position of the coil. And one way to think about that is it's some function of time. As time changes, so does theta. It's some function of how quickly the coil is turning. That's given by the frequency of the coil, or F. In other words, if the coil is turning 1 time per second, then the angle theta goes from 0 to 360 degrees in 1 second. It's back to 360 is 0. So it goes 0, 90, 180, 270, 360. Or if you like 0, pi halves, pi, 3 pi halves, 2 pi. And again, 2 pi is the same as 0. And we're going to be using radians rather than degrees when talking about rotations of coils. So I'm going to call this 2 pi ft. That's going to be what theta is equal to. So I can rewrite this expression as, for the flux, as phi equals B times A times N times the cosine 2 pi ft. And you can test this. Like if f is, like I said, if f is 1 cycle per second, then in 1 second you're going to be back to cosine 2 pi, which is cosine of 0, which is 1. You'd be back to the maximum amount of flux. So if you plotted this, it would look like a cosine function that repeats with a frequency of 1 second. That's what this would look like if f were 1. If f were 2, it would be a frequency of 2 seconds, and so on. Now Faraday's law says that if we want to find the voltage, we need to take this flux and take the first derivative of it with respect to time and put a negative sign in front of it. So okay, I'll start with the easy part, negative sign. And these are all constants with respect to time. The magnetic field isn't changing in our problem here. The area of the coil isn't changing. It's rotating, but that's taken care of by this term. And the number of coils isn't changing. So I can say VAN, or NBA if you prefer. You can rearrange these as you like to make whatever acronym you want. And then the derivative is going to go to the cosine. So I'm going to say that it's ddt, sorry. First derivative with respect to time of cosine 2 pi ft. All right. Next step, minus BAN. First derivative with respect to time of this, well, the first derivative with respect to time of the cosine is the negative sign. But the chain rule says that then I have to take the derivative of whatever's in the argument of the cosine function. If it's 2 pi ft, the first derivative of that with respect to time is 2 pi f. So what I'm going to get out here then is I'm going to get a 2 pi f, and I'm going to get a negative sign 2 pi f t. All right. Now these two negatives are going to cancel each other out. So my final expression for the voltage across the coils when they're spinning with a frequency f and a magnetic field of strength B is 2 pi f times B times A times N times the sine of 2 pi ft. So the faster it's spinning, the higher the voltage is going to be, which kind of makes sense because the faster it's spinning, the greater the change in flux with respect to time. And this is also a sinusoidal function. This is an AC voltage. It's a voltage that's changing with respect to time. And this is really why we have AC voltages. And on the PowerPoint slide, I actually plot what this function looks like. And we're using 60 hertz voltage. So the frequency at which the voltage is changing is 60 hertz. You've probably heard of that before. That's because the generators that are creating this are spinning 60 times per second, and therefore creating this voltage that we see here. All right, I hope this helps you think about Faraday's law. And the next little piece I'm going to talk about is transformers.